In the last subsection on parallel algorithms, we'll look at the sorting problem again as an example where immediate tricks to parallelize it don't work. It's not an embarrassingly parallel problem. But with the preparation from these primitives from the previous section, we can get something that is useful in practice and is indeed used, for example, in the Java library. Well, let's start from first principles. We've seen two key sorting algorithms, right? Quicksort and merge sort. So there's other sorting algorithms out there, but these are the efficient ones. So that's the two candidates that we could try to parallelize. Merge sort is a little easier, so we start with that one. Now, first of all, it's a recursive algorithm. It's a divide and conquer method. So whenever you do some recursive calls, these are independent. You can do them in parallel. That will introduce a new piece of pseudocode notation where I'll just write in parallel and then two recursive calls. Again, depends on the actual programming language how to do this, but that's something that is even better supported than these parallel loops. But that doesn't get us so far. So if we only parallelize the left and right recursive calls, we still, at the very last step, we have to merge the first half and the second half of the array into the final output. And that takes linear time. We've seen the merging method in detail back then in Unit 3. Unless we somehow parallelize the merging as well, the best we could hope for is go from time n log n, standard merge sort sequential, to big O of n maybe. But we're stuck with that if we don't parallelize the merging step. So in particular, the method that we've seen there, just to remind you, how did we merge two sorted runs? We started with a pointer at the minimum, and then we compared those two. The smaller one goes to the output, and then that pointer moves one forward. And if that one's smaller now, that goes to the output, moves one forward. That doesn't seem to work well in parallel, because again, it's like for the summing up all the, for the sequential prefix sum, every next step seems to depend on the result of the previous step, so I can't do that independently. So we have to find something else where we do treat elements entirely independently. We can do that by conceptually splitting merging into two steps. What merging does conceptually is two things. It finds for each element where it should go in the merged output. And the second stage is it rearranges the elements so that they end up there. In our sequential algorithm, we do the two things interleaved. We always put one element at its final position and then move on. And we only ever find out where an element goes just before we put it there. But we don't have to do it that way. We can split these two things. So if we look at that in more detail, say we pick some element x in the sorted output, then okay, from this picture that I was always drawing in the sorting unit, x could be somewhere here. And now the question is, where does it go in the sorted output? Where does it go? Well, it goes at the position of its rank, namely the number of elements that are smaller is its position, plus minus 1. How many elements are smaller than x in this run? Well, that's exactly the position in that run, because it's a sorted list. In here, we don't know. We have to search where x goes. But there's some position where x would fall if it was inserted into that run. How do we find that position? Well, we can do a binary search. So the overall position of x in the sorted output is the sum of the number of elements that are smaller than x in the left and in the right run. And 1 we get for free, because it's the position where that element is located. And for the other, we need one binary search in the other run, starting in the middle, and then you've seen it in more detail in Unit 2. So with the binary search, we can find where X needs to go. But then we just do this in parallel for all the elements, save where they should go, and then put them there in the second step. And in code, that looks like this. So let's go through this in a little detail. First of all, the simple part is the parallel recursive calls. So that almost looks like standard merge sort with two small twists. First of all, like in standard merge sort, we find the middle point. That's where we split. We're not doing peak sort, right? Then we can do in parallel the two recursive calls. And remember, we have to pass a buffer around, and the convention was that we use the buffer, but the sorted result at the end is back in the array that the unsorted elements were in. Then we call parallel merge. Well, we'll come to that in a second, which leaves everything in the buffer. So we have to copy it back afterwards. And this last part, this we can do in parallel by a simple loop. I just take every loop iteration, takes one element from one array, copies it into the other one. That we can do in parallel. Now for the merging itself, we first determine the rank of each element. And for that, we do the elements in the left run and the elements in the right run separately. First, we do the ones that are in the left run. So we know how many elements are smaller in their run, and we add the result of a binary search. So here I'm assuming that this binary search returns exactly the number of elements for searching this element in this array. Now the binary search we do sequentially. There's no fancy thing happening parallel-wise. And then we do the same thing again, just the mirror image. We go through all the elements in the right run. We add their rank in the right run, which is just the position, and we do the binary search in the left run. And once you know so here I could have split this up into a second round, but once we have the loop here as well, we can already write them to the buffer array at this point. So how fast is this? Because we don't do the binary search in parallel, it'll have log n, span, and work, exactly. And n is the length of the array. So if we have parallel merge on something of length n½ and n½, then we'll have log n span for each binary search. We have constant time for the writes, and we do the rest in parallel. So the overall span of the merge is log n. Now, if we analyze the work, we have to do this binary search for each of the elements eventually. So it'll be n log n work. So we're not work efficient, right? Parallel merge needs n log n work, but we could do the standard merge in linear work. But at this point, we'll leave it with that. So we get log n span for the binary search, but the overall work for one merge is n log n. Now, what happens with the recursions is that we start with the entire array, then we recurse on the two halves, and we keep going like this until we have individual elements. We've discussed the recursion for merge sort in more detail back then. the depth of this tree is this log n. That's how many times we have to cut things in half. And on each of these levels, we do things in parallel because the recursive calls are in parallel. But I have to spend at most log n on each step, but actually on the first half rounds down, I have to spend theta log n. So overall, I spend log n times log n span across all the levels. Up to constant factors, it doesn't help that I get smaller inputs. They don't get smaller fast enough. So the total span for this parallel merge sort is log squared. But that's still a substantial speed up from sequential, where we had at least n log n as the running time. So even if you have a reasonable number of processors, this is going to speed up sorting a good bit. Now, we're not work efficient in the merge, which means we also won't be work efficient overall. By essentially the same argument, you also get this extra log factor. You get n log squared n as work for the overall algorithm. But again, as before, a log factor is not that bad. You can still get a good speed up with a reasonable number of processors. Unlike back then, I'll leave it with that, but it is possible to get merge down to work efficient again. There's different solutions. A relatively clean one is not completely dissimilar to our blocking method. But I still decided not to give you the details here because it gets a bit messy. So I'll leave it with the statement that it's possible. And the details are, for example, in the lecture notes from another lecture that are linked on the website if you're curious. Now, what I didn't comment on, both measures are not optimal. The work you can get down to n log n by making the merge work efficient. The span is also not perfect because it's also log squared, and you can't get it down to log n. But that algorithm is even more crazy, so we're not discussing it. But I guess it should be as a comment here. So the combination is possible on the appropriate PRAM model, but the algorithm is substantially more complicated. This part, doable, just a bit too much for us, so I didn't want to do it. This is very tricky. Okay. Let's take a quick look at quicksort before I let you go. We can do the same as before. We can do the recursive calls parallel, easy. Same as before, if we don't parallelize the partition step, we won't really get down below linear time, even in parallel. So that's not going to help us that much. But we can parallelize the partitioning round as well. And we can do this by, again, splitting a recon phase and the data movement phase and doing things in parallel there. Now remember, quicksort partition, you have this pivot element, and for each element you have to find whether it's smaller or larger, and you have to put it to the left or the right. That's the two different parts. Doing all the comparisons with the pivot in parallel is easy. You can just remember the outcome, and then you're done. Moving things to the appropriate place is a little more tricky because the position where an element goes depends on how many other elements are smaller than the pivot. But that's where our friend the prefix sums come again into play. So we can do this as follows. I'll just go over the parallel partition. The code for the overall algorithm is exactly as for standard quicksort, apart from this in parallel here. So we get our pivot element. That's this one, and we swap it to the last position. Then we determine for every element in the array whether it's smaller. So this notation here means, this square brackets means if the condition is true, it's the value 1, otherwise it's 0. It's just a short way to write that. So in S of I, we store a 1 if that element is smaller than the pivot. In L of I, we store the opposite, just to have that convenient. And this we can do in parallel. It's independent, each just compared with the pivot element. Then in parallel, we can do the parallel prefix sums of both S and L. S and L are again just binary arrays. So the prefix sums essentially just count how many ones are before a certain position. And then again in parallel, we write the elements where they should go. So we do the comparison with the pivot again. And then we either use S or we use L to write the element to a certain position in the output. And here again, we make use of the fact that in this PRAM model, these things are synchronized because everything runs in lockstep. So we can just write it to the same array that things come from. We first read all the elements and then we overwrite the array, and the PRAM synchronizes that for us. So that's the details here. First find where elements go and then move them there in the second step. Same as for the merging step. That's the key that we had to split to parallelize things. Because we use the parallel prefix sum, we inherit the logarithmic span. What we can get this time, though, is linear work. So we get an overall algorithm with n log n work without any tricks that I didn't show you. So it's work efficient overall, at least in expectation. And the same span as for merge sort. We have logarithmic span for each partitioning step. And in expectation, we have log many levels in the recursion tree. And so that multiplies again to log squared n. Let me just finish with what I already mentioned. You can get this more sophisticated method that's work efficient n log n span on the crew PRAM at least. But that algorithm is not very practical. If you want to put this in practice, you have to work on reasonable chunks of the subproblem. Otherwise, the synchronization is too much overhead. And you can see some examples of that in the Java library. There's arrays.sort, which is a standard sorting method, but they also have arrays.parallelsort. And they're essentially using the merge sort I've shown you, with a few extra tricks to avoid too small blocks of things. But this is basically based on that.